Carlos Hoyos. Remember, if you ask a question, give me 3 seconds to get there with the microphone, okay?
Okay. So yesterday we saw how to model some of the properties of QCD in a holographic model, like confinement and a mass gap. So now we are going to talk about the physics of flavors. So we're going to do flavors in holography. Okay, so the standard realization is to consider D-brain intersections. Okay, so before taking the near horizon limit, one has a stack of some DP brains, NC of them, that we denote as the color brains. Okay, so the gauge theory is living on these color brains and is SU NC super jammels. No? Now, to this construction, we add other type of brains. That intersect along some directions, the DP brains. So we call these DQ brains. They can be of different dimensionality than the DP brains. And these are the flavor brains. And we have NF of them. So there is a SUNF group here as well. Now, if we consider strings that have both endpoints on the DP brains, that corresponds to degrees of freedom in the adjoint representation of this color group. And if we consider strings with one endpoint on the DP brain and the other on the DQ brains, then this is in the fundamental representation of this color group and in the anti-fundamental of the flavor. This will be the flavor group, or vice versa. Okay, so this means that we are adding degrees of freedom in the fundamental representation to this theory living on the DP brains. Okay, so this corresponds to the flavors. Now, let's say the first construction of this type that people consider is the D3, D7 intersection. Okay, this was made by Katz and Katz not too long after the correspondence was formulated. And then in the flat space-time, the intersection looks like this. So the D3 brains are the color brains, and the D7 brains are the flavor brains. And then the D3 brains are extended in the time and 3 space directions, and the D7 brains are extended on the same directions, plus 4 directions more. Okay, so this will be, the ignite direction is a plane transverse to both types of brains. Okay, so you see here that there is a 3+1 dimensional intersection. And the low energy effective theory that lives on this intersection is an n equals to super QCD kind of theory, where the adjoint matter has the content of n equals 4 super jam mills. No? It's coming from the degrees of freedom that live on the D3 brane, so it's just n equals 4. And then the fundamental matter is grouped in n equals 2 hypermultiplets. Okay, so introducing this D7 brane breaks the supersymmetry from n equals 4 to n equals 2. Now, we're going to take a larger limit on the number of colors, fixing the number of flavors, okay? So we take a large C limit where NC goes to infinity, NF is fixed. Okay, this is called the top limit. There is an alternative to this, which is take NF going to infinity in the same way as NC goes to infinity. That will be the Veneziano limit. Now, in this limit, we can replace the stack of D3 branes by the holographic dual. So the D3 branes have a holographic dual description by ADS5 cross S5. Type 2B string theory on this geometry. And then the D7 branes become probe branes inside this geometry. Okay, so by this we mean that they don't back react on the geometry. We just put them there, but they don't affect to the geometry or the closest string sector. Okay, so now if you want, the color degrees of freedom are described by the gravity fields inside this ADS5 cross S5. And the flavor degrees of freedom are described by the modes that live on these D7 branes. Okay, so what is the action for the D7 branes? Which fields do we have in these D7 branes? So we have the action, we write it as the number of flavors. We're going to assume that all the D7 branes are on top of each other, so we just have an overall factor. There is the tension of the D7 brane. And then the D7 brane has 8 dimensions, so this will be the work volume coordinates. And then we have the usual dBi action with the determinant of the induced metric and this gauge field strength here. So we have a gauge field living on the D7 brane. And then we have the embedding functions. That describe the profile of the string. Of the D brane. And then the induced metric is defined from the background metric and these embedding functions. So this will be the background. Okay, so if you want the numbers, the tension of the D7 is 2 pi to the 7 gs ls to right. Okay, so this action with these fields describes the dynamics of the flavor in the holographic dual. No? So having the gauge field, this will be dual to U1 current. And then these other fields, the embeddings correspond to some operators with flavor. Okay. This will be like the U1 baryon current, the abelian part. Okay, this can be generalized to configurations where this is non-abelian, or the D7 branes are not on top of each other. Even this can be non-abelian, but this is a more complicated action that we're not going to discuss here. Okay, so now this is going to tell us what kind of embedding we have to have for the D7 branes inside this geometry. So let's try to find this embedding, because this encodes the properties of the flavor in the dual field theory. So we have the ADS5 crosses 5 metric. Which I'm going to write as in this form. Okay, this is the 5 sphere, and the dilaton is constant. So we have already extracted G string here, so we can just put it to 0 and forget about this factor in the dBi action. Okay, so this is just trivial. Okay, so it is convenient to reorganize this metric in such a way that the embedding of the D7 brane appears in a simpler way. So as we see from the table over there, the D7 brane is intersecting the D3 branes along all these directions, the field theory directions. And then it's going to be extended in the radial direction as well. And then there are 3 extra directions in the D7 brane that are in the internal part. So it's going to wrap some 3 sphere inside the S5. Okay, so the D7 is going to have these 3+1 directions, then the radial direction, and then here a 3 sphere inside the S5. So it's 4, 5, 8. Okay, so we want to have here a 3 sphere. We could just write this metric for the 5 sphere in using angular coordinates and make the 3 sphere explicit here. But there is a better way to write this metric for this problem. So we're going to do the following trick. We take the radial part and the 5 sphere, and then we extract an overall conformal factor. Okay. And now this is the metric of a 6-dimensional flat space in spherical coordinates. No? So we can say that this is as in Cartesian coordinates, this will be just a flat metric like this. And this EU square is the radial direction in this plane. Okay, so now this looks like we have combined the 5 sphere and the radial direction in such a way that looks like this part of flat space, right? These 6 directions. And then this means that the D7 brane is going to be localized in a 2-dimensional plane inside these 6 directions. And it's going to be extended in the other 4. So maybe here. So we split R6 into R4 times R2. Okay, and then we write the metric for the R4 part as in spherical coordinates. And we write the metric of the R2 part in Cartesian coordinates. Okay, and the original radial coordinate in the ADS5 geometry is related to this radial coordinate in the R4 and the Cartesian coordinates in this way. Now, the D7 brane is going to wrap the x mu directions, as we said, and then it's going to be extended in the radial direction, and it's going to be wrapping this 3 sphere. Okay, and then we can choose the embedding in such a way that it sits at a fixed value of one of these 2 coordinates. So we can choose that is just at z equals to 0. And then the embedding is just given by a function that depends on this radial coordinate, y of r. Okay, so that can describe the profile of the flavor brane. So if I have a plane where these are the y and z directions, and let's say this is the radial direction. Let's say this is r equals to 0. So we can think of the D3 branes sitting at the origin of this plane at r equals to 0. And then the D7 brane is at some point here, and then extends in the radial direction, like this. Okay, so it can be coming closer to the D3 branes or coming farther away or just a straight line. Okay, so now we want to identify, well, first, what kind of profiles we can have for the D7 brane. And second, what is the field theory dual operator to this embedding field, okay? To establish completely the dictionary. So we can take now this to find the induced metric on the D7. So this will be U is replaced by R squared plus Y squared. So there is the part parallel to the field theory directions. And then there is the part that is coming from the sphere and the radial direction. So it's wrapping the radial direction in R4 and the 3 sphere, and then there is a contribution. That is coming from this part of the metric when we do the pullback with the embedding. So this will be the induced metric, and then we compute the determinant and plug it in the dBi action. Okay. So that gives.
Carlos, a question.
Yeah.
So you are choosing Z equals 0?
Yes.
It's a choice. How do we know the brain would like to stay there?
Well, there is a symmetry of rotations around this plane.
Mm-hmm.
So, yeah, if there is a solution at fixed set, then you can relate it to solutions at different sets just by rotation.
Thank you.
Yeah. Okay, thanks for the question. So, in other words, like these angular directions will be a flat direction. So, okay. So if one computes the action, one has something proportional to the volume of the 3 sphere after integrating on those directions, then the integral in the field theory directions, and then the integral over the radial direction. Okay, so this will be the D7 brain action. Okay, so we can take, this is just a constant factor, so just take some Lagrangian to be r to the cube, the square root of 1 plus I prime square. Okay, so now, because the action doesn't depend on y, only on derivatives of y, this is a cyclic coordinate. And then the equation of motion reduces to that the derivative of the Lagrangian with respect to y prime is equal to a constant. Okay, so we can write this in the following way. Taking the derivative is trivial. And we call this constant R0 cube by matching the dimensions. And then if you solve for y prime, then you get a simple form of the solution. Which is this one, okay? So now, if R0 is non-zero, then the profile of the D7 brain will be similar to the one we have for a Wilson line, which is connected. Yes?
Whenever we include flavor brains in the setup, then we embed the flavor brains in this probe approximation. So what will be the effect of flavor brains when we include the flavor brains similar to the color brains in the setup instead in probe approximation?
Sorry, I didn't.
Okay, so here we have included flavor brains in probe approximation, right?
Yeah.
So what will be the effect of flavor brains on the dual field theory when we embed the flavor brains similar to the color brains, not in the probe approximation?
Yes, so then you have to consider the back reaction on the metric and the rest of the gravity fields, okay? If you do it with localized brains, it's a very hard problem because, well, you have localized sources in the bulk, right? But you can do smearing in the internal directions, like Carlos, for instance, was one of the first doing that. And then you can find supersymmetric solutions and so on. The geometry is modified. And then in this case, in this particular case, what happens is that adding flavor branes, so when you add flavors to the dual field theory, the beta function changes. It becomes positive. And that means there is a Landau pole in the ultraviolet. So in the gravity dual, you see some kind of singularity in the ultraviolet. So when you go to large values of the radial coordinate. Okay, so there are some ways to deal with this Landau pole. But you can also do a similar thing in other situations, like you can add flavors to AVGM, for instance, and then there is no singularity in that case. But you can also do back-reacted flavors in that case as well. Yeah.
I have a question on the this DBI action of the flavor branes. So in most of the cases, for example, when we want to study the meson in the QCD, then we consider the fluctuation of bosonic fields, right? Some F alpha beta.
Yeah.
So why do we not care about the fermionic fields, fluctuation of the fermionic fields? Like so if we consider the fluctuation of the fermionic field, that will be like Messino in the QCD. So how we can understand Messino from the brane perspective? Like here, this quark correspond to the string between the D3 and D7 branes. So how we can understand Messino in the brane picture?
Yes, I only wrote the bosonic part of the action, but this is a supersymmetric theory, so there are also fermions.
Yes.
That I didn't write.
Yes.
So you could consider also perturbate excitations of these fermions on the brane, and that would correspond to these fermionic flavor degrees of freedom.
Okay, so do Messino have like interpretation similar to the string attached between these stack of D branes?
Yeah. The modes on these strings can be bosons or fermions, so they include all types of flavor degrees of freedom.
Okay, thank you.
Yeah. Okay. So if we look at this profile, it looks similar to the Wilson line. So it will be something like this. Let me erase this. You will have so I'm just plotting, let's say, the y direction here and the r direction here. And this will be the value of r equals r naught. So this part corresponds to y prime positive, and this part corresponds to y prime negative. And here you see the square root singularity that corresponds to this becoming tangential to this constant r line. No? Okay, so now what happens at the boundary is like you have a D7 brane here, but here the brane is coming with the opposite orientation, so this is an anti-D7 brane. So if you were going to consider this configuration, this breaks completely supersymmetry. So this is non-supersymmetric. So this means that the only supersymmetric case is when R naught is 0. So this means y prime is equal to 0. So the embedding is just that the D7 brane is at a constant position in the y direction. Okay, so that's the supersymmetric embedding. So in this plot I had before, we just have the D7 brane falling straight and keeping the distance with the D3 branes. Okay, so this will be the supersymmetric embedding. So, yeah.
Could you repeat why supersymmetry is broken in this configuration?
Yes, so the D7 brane is this object with some orientation.
Mm-hmm.
And when it goes back to the boundary, it has the opposite orientation. So that means it's an anti-D7 brane. Okay, you can do a more rigorous calculation, which is compute the kappa symmetry and check which solutions are actually supersymmetric. And then you get the same answer, that the y is constant. Okay. But this is a quick way to see it.
Thank you.
Okay, so with this profile, the induced metric of the D7 is quite simple. Okay, so where this is just the constant. So you see that if y0 is 0, then the metric is just ADS5 cross S3. So this means that we have a CFT in the dual field theory. Okay, because if we look at excitations on the flavor brane, they are going to have the properties of excitations of the gravity modes on ADS5. So it's going to look like a CFT. Now, this is because we are neglecting the back reaction. So this behavior is also valid when R goes to infinity. Right? Then we can neglect the I0 part. So asymptotically, the induced metric on the D7 brane is an ADS5 geometry. So when I0 is different than 0, and we take the opposite limit, R going to 0, then we see that these factors become constant, right? These conformal factors become constant. So we have just Minkowski spacetime here. And here we have R4 in spherical coordinates. And when R is going to 0, the 3-sphere is going to 0 size. But because this is like R4, this is smooth. So the 3-sphere collapses smoothly. Okay, so the embedding for y0 different from 0 can be plotted in this way, where this will be the 3-sphere, this will be the radial direction. Okay, so it's like the cigar geometry, but instead of having a circle, we have a 3-sphere. So you can imagine that when y0 is different from 0, there is going to be a mass gap and a discrete spectrum of excitations, okay? Because this induced metric has the same properties as the cigar. Okay, and when y0 is equal to 0, the spectrum is gapless and continuous. So this will be gap spectrum. Okay, so there is this curious thing of this model that you can have something which is a CFT in the adjoint sector, because you just have the ADS5 cross S5 geometry. But in the flavor sector, you can have something which looks confined in some way, or at least with a mass gap. So now that we know what is the embedding, let's establish the dictionary. So Okay, when we go to r equals to 0, we have the D3 brane sitting somewhere here, and the D7 at some distance, why not? Okay, so if we extend a string between the D3 and the D7, it's going to have some energy because it has finite length. So we can try to identify that as some mass of the quark, right? So this will be one endpoint on the D3, so it's in the fundamental representation of the color group. So the quark mass equals the string tension times the length between D3 and D7, or the separation between D3 and D7. So this is just giving us a formula like y naught is the separation over 2 pi alpha prime. Okay. So, okay, you might worry that we are in curved space-time, and this looks like the formula you will use in flat space-time. But if you actually do the exercise of computing the energy of this string, you see that the conformal factors cancel out. So in the end, it's exactly this formula in this ADS5 geometry. Okay. You can do this easily. So now, to do the holographic dictionary, we are going to write y as y0 plus a perturbation. And then you follow these steps. You find the induced metric. So you have that the induced metric is going to be the background metric that we wrote over there, plus some perturbation. This perturbation is quadratic in the perturbation of the embedding. And then you can compute the determinant. And expand to quadratic order. Okay, so that gives you an action for the perturbations. Okay. Which is like this. Will be some factors of the tension and so forth. So I'm assuming there is no dependence on the directions of the three sphere. Sorry. Okay. So it will look like this. We're interested in the behavior when r goes to infinity, right? So maybe it's simpler to look at the equation of motion. So the equation of motion is just this thing. That's very easily computed. So this will be the flat space-time in the Minkowski directions. And then when R goes to infinity, this becomes something like this. Okay, so for a canonically normalized field, in ADS5, the equation of motions will be like this. Okay, so we see that there is a discrepancy in the first derivative term. And that needs to be corrected. No? We say that the induced metric asymptotically is ADS5. So in order to make the dictionary, we need a field that has the canonical normalization. But this can be easily compensated just by defining dy is r times phi. Okay? So the embedding function is not directly the field dual to the flavor operator, but it's this phi field. That's the dual. And when you do this change, you find that the mass square equals -3. So the dimension of the dual operator is 3. Okay. So because this field doesn't carry the non-abelian part of the flavor indices, it's just diagonal in the flavor, then the natural operator is the quark condensate. Okay, so in the supersymmetric theory is a bit more than this. There is an extra piece which is dimension 3 made out of the scalars, but essentially, morally, it's just the quark condensate. If you do the boundary expansion, then you find that this field has as normalizable and non-normalizable contributions, the expected behavior. So, well, the dual operator is just Q bar Q. So phi, when R goes to infinity, goes like Y0 over R plus some constant over R cube. Okay. And then you can identify this coefficient with the source for this operator. That's the quark mass. So it gives us precisely the same formula that we wrote before. Okay, so the calculation of this string that is extended between the D3 and the D7 gives the same value for the quark mass as this calculation using the holographic dictionary and the asymptotic expansion. And then the quark condensate is V is proportional to this V. So you see that in the supersymmetric embedding, the quark condensate this V is 0, so there is a 0 expectation value for the quark condensate. Okay, and this you can understand because, in principle, in the Lagrangian of the dual field theory, there will be a term which is like the mass times the quark condensate, the quark bilinear. So if this had an expectation value, that will change the energy. It will increase the energy above 0. So because you are in the supersymmetric vacuum, this is 0. Okay. Well, so if you introduce, well, any questions about this? No? Okay, so if we introduce the probe D7 branes in a geometry which is a black brane geometry, then we can do follow similar steps. Okay, so there is some change of coordinates. So, well, maybe I have time just to write it. So this is the black brane geometry. So it's the ADS5 black brane. So there is some change of coordinates where rho squared equals u squared plus this. This f of u is 1 minus u(h) to the 4 over u to the 4. So if you do this change of coordinates, then what happens is that you can again put this in the form of flat space metric. Okay, and then you can follow the same steps for the embedding. It's just more complicated because there are extra functions appearing in the metric. So it's not going to be true that the embedding now is a cyclic variable inside the action. But then you find that if you plot the RY plane, where R and Y are defined in the same way as there, the black hole horizon is along a circle at UH. So here, inside here, we have the black hole. And then, in the absence of this black hole, the supersymmetric embedding is just Y is constant. And now what happens is the black hole is attracting the embedding. Okay, so if the embedding is far away, starts far away in the ultraviolet, then it bends towards the black hole, but it reaches R equals to 0 before touching the horizon. But if it's close, if it's closer, then it can just fall inside the horizon. Okay. So this kind of embedding is called Minkowski. And this kind is called black hole embedding. When this happens, there is an induced horizon. Okay. So here, the spectrum is gapless and continuum in the same way as it is in the ADS5, or it was in the Witten model where you are in the high temperature phase with a black brane horizon. Okay, so this Minkowski is gap discrete mesons, discrete spectrum. Of mesons. And here in the black hole embedding, we have something which is gapless. Continuum spectrum. Okay, so people refer to this as that the mesons that you used to have here, when you increase the temperature, they melt. And then you have some completely deconfined degrees of freedom for the flavor. So if you want, the quarks are liberated from the mesons in this black hole embedding. No? So the point where this happens depends on the ratio between the temperature and the quark mass. And you have to do this numerically, okay? You cannot find these embeddings analytically, so you have to use numerics to do this calculation. And it happens that, well, in principle, you can interpolate continuously from this Minkowski to these black hole embeddings. Now, there is a point where the brain will be just touching the horizon. That will be like a continuous transition, like second order. But what happens is, if you compare the action of these embeddings, when you increase the temperature, there is a point where the black hole embedding has a lower action, and it becomes dominant, and there is a jump between the Minkowski and the black hole embedding. So it's a first order phase transition again.
A question?
Yeah.
So remind me this thing. So in that case, in the SUSY case, it was Y0 the one that was giving the scale, right? So the masses, they come with Y0. That happens also in the Minkowski embeddings. Why here, if you have the temperature of the black hole, why suddenly you have the possibility of having something like gapless, etc.? Is it this induced horizon on the brain that produces it?
Yeah, it's the induced horizon.
How it produces it? How it happens?
So, well, if you look at this Minkowski embedding, then it will have this topology I wrote before, like it just closes like this. And then in the black hole embedding, what will happen is that the 3 sphere doesn't collapse to zero size. Instead, here you'll have a horizon. Okay, and then it's the same physics as in a black hole. Yeah. So, yeah, so the transition between these two happens at where MQ is given by, so the critical temperature is related to the quark mass with this numerical factor of 0.92 times this factor that depends on the Toff coupling. Okay, so this is, you just have to do this calculation numerically to find this.
For this critical temperature, you start increasing the temperature of the black hole, and then you see when the embedding jumps. Is that the calculation?
Yeah.
Okay.
For every Y0, you have several embeddings, some of them outside and some inside, and then you compare the action.
Y0 is the MQ, and
yeah.
Very good.
Yes, thanks. And then, because this is bending, this means that this subleading term is non-zero in these embeddings. So in both cases, the quark condensate is different from zero. Okay, so this means that there is a spontaneous chiral symmetry breaking as well as the explicit breaking by the mass. Finally, the massless embedding is just straight. So the induced metric is just the ADS5 black brain geometry for the massless. embedding. So without a mask, there cannot be a phase transition. Okay. So yeah, I think this is a good place to stop. Questions? Yeah. I still have an hour. Okay,
Yeah.
sorry.
There is a question in the chat
Okay.
that says, where is the D3 brain in the black brain geometry? I don't know how to interpret it, but okay.
Well, you can think that the D3 brains stay behind the horizon. They're covered by the horizon. Okay. Yeah.
Maybe I'm just confused by the terminology and everything. So this may be a very naive question.
Yeah.
So how much of the... So what should I think about this theory? Is like this, how much of QCD is this theory is, or how much of an analog theory to QCD this is? I'm kind of a bit lost on this point.
Yeah, so, okay, let's say, the adjoint part is far from QCD because the adjoint part is just a conformal field theory. Okay, so that is very different from QCD. Now, the flavor part, if you have a mass, then it mimics something, some property, no? Like you have a discrete spectrum of mesons, for instance. Still, it's not like QCD, because in the absence of temperature, there is no quark condensate, and in QCD there is, right? So the thing that maybe is closer to QCD is when you're at final temperature. Then, in this case, for instance, if you have the black hole embedding that resembles the high temperature phase of QCD in the sense that you will have deconfined flavor and adjoint degrees of freedom. And as we know, for some properties of the quark-gluon plasma, it's not so relevant that this was a conformal field theory, like the shear viscosity doesn't care so much whether the theory was conformal or not. So maybe that kind of phase is closer to what you could expect from QCD. And then in QCD, one observes that heavier mesons, so the mesons are also dissociated in the quark-gluon plasma in QCD, and one observes that mesons made out of heavier quarks take longer to dissociate. Okay, so this is this resembles that property as well. That the heavier the meson is, the higher the temperature has to be to the mesons to be melted. So, okay, but yeah, quantitatively, it's not. Yeah. Good. So this means I can talk about Sakai. There are more questions about this? No? Okay, so let's go to a more realistic model, which is the one we discussed before, but we are going, the Witten-Jamils model, we are going to add flavors to it. Okay, so yeah, concerning this last question, there is another aspect which is unlike QCD, which is, I didn't mention this, but there is just a single gauge field on the D7 brane. That means that for the D3, D7, the flavor group is just U, NF, the vector part. Okay, in QCD, what happens is that we have a UNF left times UNF right, which is broken to UNF vector. Okay, so there are, well, both. So there is some spontaneous breaking doing this thing, right? And this is not captured by the D3, D7 model, okay? Because the axial part of this symmetry is already broken at the level of the Lagrangian by some couplings in the axon, okay?
So in this sense, what you call chiral symmetry there is not what the QCD people call chiral symmetry, right?
Yeah. Yes. I mean, there is okay. There is the symmetry that corresponds to rotate around the D3 branes. Yeah, that's some kind of R symmetry that also rotates the fermion like a chiral symmetry, but it's not exactly the same as what people mean in QCD. Yeah. Okay, so adding flavors to the Witten model gives the Witten Sakai Sugimoto model. Okay, so this is the following configuration. We have the D4 brane with supersymmetric breaking conditions on the circle. And then we add the D8 and anti-D8 branes. Okay, so there will be NC of these ones and an F of these ones. Now, the intersection is as follows. So this is extended along these directions, and then the dx and anti-d8s are extended in this direction. Okay, so the d8s occupy the whole spacetime except this direction along the circle. Okay. So you see there is again a 3+1 intersection. Okay, so this describes a 4-dimensional field theory with fundamental degrees of freedom related to these D8 branes. Now, this is a non-supersymmetric intersection, even without the anti-D8s. And then we have that at each of these intersections, we have fermions, chiral fermions, and they have opposite chiralities for D8 and anti-D8.
Let me ask you the question that is in the chat. So the person is following up on that thing of where the D3 brane is in the black brane geometry and saying, how do you compute the length of the string between D3 and D7? Is talking about the mass parameter, etc. I think.
Yeah, then you don't compute it in this. It's, you will read the mass for the asymptotic behavior.
Exactly. Yeah. Thank you.
Yeah. Okay, so now we have chiral fermions left and right. So I don't remember which one is in which intersection, but they have the opposite chiralities. And then at low energies, this flows to SU NC Jamils plus NF fundamental fermions. So this is really flowing at low energies to QCD with NC colors and NF flavors. As before, there is no separation of scales between the Kaluza-Klein modes on this circle and the mesons and glue balls in this theory at a strong coupling. Okay, so it's the same thing. So one finds that the lambda QCD of this theory is of the order of the Kaluza-Klein mass. so at a strong coupling. So that still is true. Okay, but still we can try to extract some properties of the theory we're interested in. Okay, so because we have two different sets of 8 branes, we have a flavor group, which is the same as for QCD. UNF left times UNF right. Okay. So that's coming just from the gauge groups on the D8 and anti-D8. And then what happens is that if we were to put these two guys together, they will just annihilate and produce radiation and disappear. Yeah.
I didn't get what do you mean by these the 8 bar brains?
It's anti-brane.
Anti-brain. And what does mean?
It means that they have the opposite orientation, and so this preserves half of the supercharges, and this preserves the other half. So altogether, they break all supersymmetries.
Okay. But from the point of view of the, let's say, the embedding, they are like the same.
So I haven't talked about the embedding, but well, I will talk about this in a moment.
Thank you.
Yeah. So I haven't gone to the holographic dual yet, just describing this brane configuration. Okay, so yes, so these are like objects with opposite charges, no? So when we put them together, they annihilate each other. When they are separated, if we fix the separation, they still attract each other. No? We fix them by some boundary condition, if you want. And there is some mode which is tachyonic in between the two of them that you can stabilize by separating them. But you can still have a situation where they just start having here condensing strings between the two of them, and eventually they join like this. So it will be some kind of funnel joining the D8 and anti-D8. Okay, and then they become like a single object. Okay. So you can imagine, no? You have two different surfaces, and then they create a funnel between them. Okay. And when this happens, then you are doing some breaking of this group to the diagonal group. So this will be the spontaneous symmetry breaking of flavor. No? So this is the weak coupling picture. You can do this more concrete. If you write the action of these D8 branes, then there is some field which is like the tachyon field. And then when it acquires some expectation value, then it couples the chiral fermions in such a way that you get Dirac fermions which are massive. Okay, so that's roughly speaking what will happen. So now we go to the holographic dual. So the D4 branes become the Witten geometry. That, if you remember, this direction where the D4s were extended now collapses to 0 size in the radial direction. So I was calling this U and tau. And now, having the D8 and anti-D8 in some position here before taking the near horizon limit of the D4 branes means that the D8 and anti-D8 will sit at some position along this circle asymptotically. Okay, so we can have the D8 here and anti-D8 here. They have to extend towards the interior. But here, there is no place where they can end. No? They cannot end in empty space. So the only possibility is that they join. Okay? So if they join, the situation in the holographic dual is similar to this situation at weak coupling. So this means that there will be a spontaneous breaking of the flavor group, so spontaneous chiral symmetry breaking. So having this geometry means that in this case, confinement implies chiral symmetry breaking. Now, if we look at the action of the D8 branes, no? Now we will have a single object. So it has an action which is similar to the one of the D7, just dBi with the tension of the D8 brane. So now the dilaton is non-trivial, so we have to take it into account. Okay, so in particular, there is this field, which is dual to the flavor symmetry. But now there is just one gauge field. So where did the axial part of the symmetry went? No? So the way to understand this is to look at this embedding more closely, and we realize that, in fact, this has two boundaries instead of one boundary. Okay, so that's the key for the apparently missing symmetry here. So the easiest thing is to use the so-called antipodal embedding, where we just take the D8 and anti-D8 to sit at opposite sides on the circle. Okay, so in this picture, they will be sitting just opposite. And then this embedding goes through the origin here. Or if you plot it like a disk, you flatten this, then the embedding just crosses through the disk. Okay, so this will be D8 anti-D8. So we can make some change of coordinates that is convenient for this setup. We introduce a coordinate r, and we replace the coordinate tau by some theta. And then we are making these polar coordinates on this plane. So r equals to 0 corresponds to this point. Then we use Cartesian coordinates. To parameterize the plane, and then the embedding is just that y is equal to 0. Okay, so now the D8, yes.
Thank you. So this is a bit of a naive question, but is the action on anti-branes identical to that one, or is there something different, the effective action?
This part is the same, but there is another part that I didn't write, which is the coupling to the Ramon-Ramon forms, which has opposite sign. That's the charge. The charge is opposite.
Okay, I see. Thank you.
Yeah. Okay, so then the D8 wraps the X mu directions, the S4 directions, and the Z direction. Okay. So the Z direction is just this direction along the profile of the brain, which is straight on this plane. And then, as you see, there is a boundary when Z goes to plus infinity, and another boundary when Z goes to minus infinity. So you have to specify boundary conditions for the gauge field on both boundaries. So the limit when Z goes to infinity, plus infinity of the gauge field on the brain is going to give you the background gauge field for the left symmetry. And the limit when Z goes to minus infinity is going to give you the background gauge field for the right symmetry. Okay. So this means that you have an axial background gauge field and a vector gauge field, which you can construct with different combinations of those. So the vector will be just the sum, and the axial will be the difference. Okay, so you see that if you make, if you take the symmetric boundary condition where L equals R, then the axial is 0. And if you take the antisymmetric boundary condition where they have opposite signs, then the vector part is 0. So modes that obey a symmetric boundary condition will be even in this coordinate, and modes that satisfy antisymmetric boundary condition will be odd in the coordinate. So even in Z corresponds to vector modes, and odd in Z corresponds to axial modes. Okay. So in particular, for the gauge field, the even part corresponds to the vector gauge field dual to the vector current, and the odd part corresponds to the axial current. Okay. So if we take the A mu Z equals A mu minus Z, this is the vector current dual. And then if we take the odd part, this is the dual to the axial current. Okay. And that's how you find the full set of flavor symmetries. Okay. Now, in this model, there are no masses. So there should be Goldstone modes associated to the spontaneous symmetry breaking. So in this case, they correspond to a Wilson line extended in the along the this direction of the D8 brane. So the Goldstone mode is just a massless degrees of freedom that you can find by looking at the equations of motion of the gauge field. So, so the Goldstone for the broken U1 NF axial are given by a Wilson line. Of this one, okay. Okay, so this, well, the nice thing about this model is that it captures many of the physics of QCD. No? It has the right flavor group structure. It produces a spontaneous chiral symmetry breaking, and it contains the Goldstone bosons. Okay, if you go beyond what we saw here, you can also see that there is a U1 axial anomaly, as in QCD, that you can find looking at the action of the brain. So it captures even this aspect of QCD. Now, in this case, there is also something like a meson melting or chiral symmetry restoration. When we put the system at finite temperature. Okay, so we saw before that the confined phase corresponds to some geometry with this kind of topology. So this was the time, Euclidean time direction. This was the tau direction, and then this was closing. Now, if we have the D8 branes, as we have said, then the D8 anti-D8 necessarily has to be a connected configuration, so there is chiral symmetry breaking. Now, in the deconfined phase, we change this topology. Now is the temporal circle which is collapsing to zero size, and the fourth direction just stays with a finite radius. And now there are two things that could happen here. So one thing is that we still have a connected configuration, like this. And then this is deconfined, but is similar to the D3, D7. The spectrum here will be gap. There is chiral symmetry breaking. So this is, there is chiral symmetry breaking. But there is another possibility, which is in the same topology for the geometry. Now, because we have a horizon, these D8s can just go into the horizon, and then we can have a configuration like this, where they just fall straight into the horizon. And now we have both, we have a gauge group on each brane. So now we have the full UNF times LF times UNF, right? So this will be, we'll have the full symmetry. So this is chirally symmetric. And so there can be a transition between this situation and this situation that depends on the asymptotic separation between the D8 and anti-D8, okay? So this is something, again, that one has to be doing numerical calculations to find these embeddings. And then what happens is that, well, I will just give you the numbers. For instance, for the antipodal configuration, it's clear that this cannot exist, okay? Because in the antipodal configuration, the brains are connected through the origin, and now we are removing this origin and opening it. So for the antipodal configuration, you go directly to this situation where you go from confined to deconfined. So both deconfinement and chiral symmetry restoration happen simultaneously. But if the brains are closer together, then there can be a separation between the two phase transitions. So the chiral restoration transition exists for a separation between the D8 and T8, which is smaller than a critical length, which is 0.97 R4. Okay. And then it happens at the critical temperature, which is about 0.154 over this separation. So, well, this is according to intuition. No? The closer these 2 points are, the less the D8 will go into the interior, so the higher the temperature has to be in order for this configuration to become favored. Okay. So, okay, so I think now this is a good place to stop. Thanks.
Questions?
Is there any equivalent to the like flavor changing currents in the gravity dual picture? Is there any equivalent or easy picture to see in the gravity dual?
Well, that will be produced by electroweak interactions, no? Flavor changing. So, no.
More questions?
So this is a small clarification. From those formulas where you define the left and right currents, I would say that naively there are like two different boundaries on which these two gauge fields live. Am I correct in saying this?
Yeah.
Okay, so when we do calculate the expectation value of any of those two currents, the vector and the axial ones, are we summing vacuum expectation values taken on two different boundaries? And if so, what does it mean?
Well, it means that here you are taking, if you look at the asymptotic expansion here, it will give you something like the expectation value of Q left, and the other will be, sorry, this is Q right, Q left, and the other will be Q left, Q right, no? So, and then you just add them because it's just the sum.
No, because I'm not, it makes me uncomfortable to see like, you know, that my naive expectation would be that like I have two different theories on these two boundaries and they should be, you know, two quantum field theories living in two different boundaries, so they shouldn't care about each other. So like taking an expectation value from one and summing it.
No, the point is this one. Is when you go to the original configuration, no, if you look in 5 dimensions, it looks like you have a theory living on this intersection and a different theory living on this intersection. They can interact through the D4 brane, but in principle, they live at different points in this direction. When you go to energies much below the Kaluza-Klein mass scale, then this circle essentially reduces to 0 size, and then they are on top of each other. So you just see a single theory. Yeah.
Thank you.
Yeah.
More questions? Okay, let's take a break. Thanks very much, Carlos.
Just a reminder, as I said also yesterday, if you have a poster for today's poster session, you can put it up now because the original poster session was at 6, but for more people to see it, it's better to put it now.